Hello guys, this is Paul McWhorter with TopTechBoy.com, and we're here today with episode number 20 in our incredible new tutorial series where you're teaching your Raspberry Pi who's boss. What I'm going to need you to do is pour yourself a nice tall glass of ice cold coffee. That is straight up black coffee poured over ice, no sugar, no sweeteners, none needed. And as you're pouring your coffee, as always, I want to give a shout out to our friends over at Sunfounder. Sunfounder is actually sponsoring this series of video lessons, and in this class we will be using the most excellent Sunfounder Raphael kit. Most of you guys probably already have your gear, but if you don't, look down in the description. There is a link over to Amazon where you can hop over and pick up the identical hardware that I will be using. But enough of this shameless self-promotion. Let's talk about what I am going to teach you today. And what I'm going to teach you about is echolocation. Okay, we are going to be learning about echolocation. What is echolocation, you ask? Well, let me explain. Echolocation is using sound to identify objects and sort of know where objects are. Okay, so instead of using your eyes, you're using sound to detect where something is. And echolocation is actually used in quite a number of different applications by humans, but it's also common in the animal world. And can you tell me two animals that are very famous for using primarily echolocation in their interaction with the environment? Okay, can you name the two? The first one is the bat. Okay, the bat lives in caves, and caves are dark, and so if the bat is going to interact and do things in a cave, it needs a non-optical way to know where things are, and that is echolocation. So what the bat does is he puts out a little chirp, and that chirp goes out, it hits an object or a target, and then it bounces back. And what the bat knows is he gives the chirp, he waits for his echo, and then when he hears his echo, he knows something's there, and also a little bit about how far away it is. And so if he chirps and gets the echo back quickly, the object is near. If he chirps and gets the echo back in a longer period of time, he knows that it's distant. And it's just really amazing how sophisticated the echolocation capability is of bats. The other echolocation animal is whales. Whales are famous for making those squealing or those moaning noises, and those noises can they can go through the water almost halfway around the world because sound really travels a long way in water, and so whales can use echolocation to very, very, very great distances. Probably for us humans, the most most familiar sort of echolocation. Here you're using radio waves instead of sound waves, but it would be radar, that you send out a radar signal, it goes out, it bounces off the target and comes back, and based on the amount of time in flight of that signal, you can detect whether something is there and how far away it is. Also sonar, okay? Submarines use sonar, and they're sending out pings. If you've ever watched one of those old submarine movies, you hear that ping, ping. Well, they're sending out a ping, and they're waiting for it to bounce off of something and come back. And good sonar operators can distinguish between, not just how far something is away, but how big it is and what it might be. And so sonar is really quite an art. So sonar is pretty important. Echolocation is pretty important, and that is what we are going to learn about today. So enough of this introductory banter and discussion. Let's jump in. And the good news is, in your most excellent Sunfounder Raphael kit, there is a device which will allow you to do echolocation, and that device is the HC-SR04 HC-SR04. Rather than giving you the model number, it would probably be a little bit easier if I showed it to you. So I'm going to go to this view. It is over here. It's that little board that has two nodes coming out, like two little cylinders coming out. That is your echolocation device, and that's the device that we are going to be using today. So I need you to go ahead and open up your Raphael kit, dig through it carefully, keeping it neat, and find your HC-SR04. Then what we're going to need to do is we're going to need to get that thing hooked up. So you're going to need a few wires. Now I show you the bond out here, but you can see that when I built it, I actually went ahead and I put it on a board. When I built it, I went ahead and I put it on a board. Give me just a second here. I need to do a little Windows management. There it is. Okay, we're good. I was talking too long and my Raspberry Pi went to sleep. It's pretty sad when your Raspberry Pi goes to sleep, right? But if you look up here, what you can see is the sensor is pointing towards you. The sensor is pointing towards you. And when the sensor is pointing towards you, let me get this. When the sensor is pointing towards you, the leftmost pin is the positive voltage. Since we're using a Raspberry Pi, that would be 3.3 volts. The rightmost pin is ground. So left is 3.3 volts, the right is ground. That is pretty simple. But pin number 2, the second from the left, is your trigger pin. And then pin number 3 is echo. So you power, you ground, and then you have a trigger pin and you have an echo pin. What we're going to do is we're going to hook the trigger pin up to GPIO pin 23, as you see here, and we're going to hook the echo pin to GPIO 24. So trigger to 23, echo to 24, and we're using the BCM numbering system. And just as a friendly reminder, this breakout board is labeled with the BCM numbering system. So that's why I like to use it. In that way, I can read the label right off of the little pins and not have to try to count pins and do calculations and things like that. So hopefully that makes sense. Now you see when I actually built it on the board here, I brought 23 over to the trigger pin, and I brought 24 over to the echo pin, and then I powered up my positive rail, my top rail. I powered up with the 3.3 volts, and then I grounded. I hope I didn't. No, I'm sorry. Up here, this is ground. I grounded here, and then I made the rail positive with the 3.3. So 3.3 volts to your positive rail, and then ground to your negative rail. And in the first few lessons, I just think it doesn't matter, so I hooked them up different from the labels, because just mentally in my mind, power was power and ground was ground. But that really, some of you guys, that really offended. So I'm sorry. I'm going back and I'm hooking things up according to the labels. And so what I have is I have the ground pinned to the ground rail, and I have the 3.3 volts to the positive rail, and then I've jumpered across. So I've jumpered a wire from ground to ground rail, so that connects the ground rails, and then the positive, I've jumpered over to the positive. So the positive rail is connected to the positive rail, the ground rail is connected to the ground rail, and that way I can snag either a ground, or I can snag a 3.3 volts off of any, either the top 2 rows or the bottom 2 rows, if that makes sense. So hopefully you have this thing hooked up. But now, how do we actually operate it? It's really very easy to operate, but I'm going to be honest with you. If we just jump in and start coding, you're just going to be copying what I'm doing. And so I want to go through a little bit of work here on my sketchbook. And with a little bit of work on my sketchbook, I want to explain to you what we're doing, right? We always want to do things on paper before we do them. We always want to do things on paper before we do them in code. And then the other thing that we always want to do, we want to use good engineering practices. We want to understand what we're doing. So if I show you how this is actually working, then you might want to do it differently, or if you saw a strange result, you would, it would help you in debugging and troubleshooting. Hopefully that makes sense. But let's jump in and remember we had what two pins? What two pins did we have? The first pin that we have is the trigger pin. The trigger pin. The trigger pin is the pin that we send signals to command the HC-SR04 ultrasonic unit to do a certain thing, and then we listen on the echo pin. We talk to the trigger pin and we listen to the echo pin. So here's the trigger pin, and then down here, I'll show this. This is the echo pin. So I have trigger and echo. And then what I have here is just time along this axis. So this is just looking as time marches across. And then here, this is the signal we apply. And so what we do is we start somewhere, and then what we do is we send the trigger pin to 0. Okay, we send the trigger pin to 0. So we're starting out at a 0. And then what we're going to do is we are going to leave that trigger signal to 0 for 2 microseconds. And 2 microseconds is 2e to the minus 6. All right, 2 microseconds, 2e to the minus 6 seconds. Okay, then we're going to come over and then we are going to send the trigger pin to a 1, to high. Okay, now how long do we stay at high? We stay at high for 10 microseconds. Okay, we're going to stay high for 10 microseconds, and then we are going to come down back to a 0. All right, so what did we do? We sent a pulse to the HC-SR04 telling it, do your thing. Okay, but we're very deliberate about it. The 0 lasts 2 microseconds. We transition that pin to a 1. We hold the pin at 1 for 10 microseconds, and then we come back to 0. Now the HC-SR04 is going to start doing its thing. So here I'll change colors because we are now going to be looking at the signal coming off of the echo pin. So blue was talk, red is listen. And you can see these are, I'll just kind of draw a dotted line here. So it's at this point that trigger pin sees that dropping edge of our control pulse, and that's when it's going to go. So once it sees that, there is going to be some period of time, and we don't know what it is, but some period of time for it to begin its thing, okay, for it to begin listening and getting all configured. But what it is going to do is it is going to send out a sonic pulse. It's going to send out a sonic pulse. All right. And when it sends the sonic pulse out, how does it know the sonic pulse has left the barn? The sonic pulse has left the building. It tells us that by sending echo high. Now it is waiting to detect the echo. It is waiting to detect the echo of the pulse it sent out. And when it hears it, it will go down. Okay, so we send a 0, we send a 0, we send a 1, and then we send a 0. Now the HC-SR04 knows that it should send out a ping. At the point that it sends out a ping, it indicates that by sending the echo pin high. Now it sits and listens and listens and listens, and when it hears its ping come back, it lets us know that the ping came back by sending the echo pin low. So if we want to measure how long that pulse was away, how long that pulse was traveling, what do we need to know? we need to know this time, the time that the echo pin was up. And that would be the ping travel time. That's how long it takes the ping to get to the target and to return. Does that make sense? So as far as what we're going to do here in the code, we need to generate this signal, and then we need to listen here, and then we need to measure that time. Okay, now if you see that, it's pretty easy, but we've got to be very deliberate in doing it. And you can't start your clock, you can't start your stopwatch at your trailing edge, because we don't know how long it takes for it to actually initiate the ping. And so you don't time from your your trailing edge, you time from the echo pin's leading edge. Does that make sense? I hope it does. Man, this is pretty cool. So I hope you guys sort of sketch this down with me, because as we are going through our coding, what we're going to need to do is we are going to need to be looking back at that. And it's going to be a lot easier to code if we look at our picture. Okay, remember, one of the things that I'm trying to do is teach you good engineering practices, and part of that good engineering practice is to think about it and get things working on paper before you try to jump in and start coding. And man, that's one of the things that so many of these lessons are so bad, is they just start showing you lines of code without really explaining to you what you're doing, and then what you're ending up doing is just copying what the guy's typing. Not here, not on my watch. I want you to learn, and I want you to be able to go out and do things on your own. Okay, I need to switch over to my Raspberry Pi view. I think now that you can see that we have this thing hooked up. Okay, so we've got this thing hooked up, and now we are ready to code. So I'm just going to come over to the full screen code view, and what I will need you to do is come down, and I gotta use the right mouse. It's very confusing having two mice, one for the Raspberry Pi and one for the studio computer. You know, I'm always grabbing the wrong mouse, but I digress. So come down to your Raspberry Pi start icon. We're going to go up to programming, and we're going to come down to Thony, and then Thony's going to open up, and I'm going to go ahead and I'm going to save this. I'll save this as, okay, I'll save this as echolocation, like that, .py, and the .py is kind of important, and boom, we're ready to start coding. We are ready to start coding. So what are we going to do? We're going to be using the GPIO pin, so we better import rp uppercase little I .gpio all uppercase. Then we're going to need to import time, because we're going to be doing a lot of very precise timing functions. Now what are we going to do? We are going to do the GPIO .set mode, and we are going to be telling it that we are working with what? GPIO.BCM numbering scheme. Why the BCM numbering scheme? That way I can just read the pin numbers directly off the Sunfounder breakout board, and I don't have to be counting pins or anything like that. So if I'm working just directly with the Raspberry Pi, connecting directly to it, I like to use the board or the physical numbering system. If I'm going through the connect or through the breakout board, I like to use the BCM. Hopefully that makes sense to you guys. Hopefully that makes sense. All right, so we've got that set up. Now we've got to tell it what is our trig pin. Our trig pin was 23. I'm looking over to make sure, yes, GPIO pin 23. And then we have an echo pin, and that was 24. Now we need to go ahead and set those things up. So I've got GPIO.setup. What do I want to set up? I want to set up trig pin, and trig pin is a what? It's a GPIO.out, like that. Okay, and then I need to do a GPIO.setup, and what I'm going to set up, I'm going to set up echo pin, and that is going to be a GPIO.in. Why? We are talking to the trigger pin, we're sending signals to the trigger pin, and then we're reading from the echo pin. So hopefully that makes sense. All right, now we need to go ahead and we need to do our try and except so that we can cleanly leave the program. So we'll have a try, and we'll come back and fill in that try later. And let's go ahead and finish it up while we're thinking about it. Except, and we want to accept out on keyboard interrupt like that, and then just open and close. And what do we want? Need a colon there like that. And then what are we going to do when we see the Control C or the keyboard interrupt? We're going to do this little bit of code, which is gpio.cleanup like that. And then to let us know that it actually executed the GPIO cleanup, I'm going to just do a print, and it's going to say GPIO good to go, like that. All right, now we need to come in and write our program. Well, you know we're going to want to do this over and over. And what I'm going to be doing is, I should probably say what this program does is, I'm just going to be sending a ping and then see how long it takes to get the echo back, to get the reflection back from the target. And so if the object is very close, that should be a smaller number, and if the echo time is very large, then it will be further away. So a small number means it was, you know, boom boom, it was fast. A larger number means it had to travel a larger distance. But you can see we're going to want to do this over and over, so we'll do a while true. When is true true? True is always true, so we're going to create an infinite loop here that's going to keep looping until it sees the Control C. Then it will drop down into the keyboard interrupt, and I hope that makes a lot of sense. Well, the first thing that we are going to need to do is we are going to need to gpio.output, right? The first thing that we did, let me switch back. Let me switch back over here, and let's look at our little picture. What's the first thing that we do? We send that trigger pin, we send the trigger pin to 0 right there. Okay, so that's the first thing we are going to do is set the trigger pin to 0. And so that is going to be a GPIO.output. What are we going to output to? The trig pin. And then what are we going to output? We are going to output a 0. So we're going to set trig pin to 0. And now what do we need to do? We need to wait. And we need to wait for how long? 2 microseconds. So we are going to do a time.sleep. We're going to do a time.sleep of 2 microseconds. Well, that would be 2 e to the minus 6, because in scientific notation, e to the minus 6 is micro. So 2 microseconds like that. So we wait. Now, after we wait, what do we do? GPIO.output. Now we're going to set the trig pin what? To a 1 or to high. Now we're going to wait again. Go look at your little drawing. We were going to leave that trigger pin high for how long? For 10 e to the minus 6, like that. Okay, and then after we do that, then what are we going to do? We are going to GPIO.output, and that output is going to be trig pin, and that's going to go back to 0. So we've sent it our control pulse, and let me go ahead and just show you what we have coded up so far. What we have coded up so far is this. Okay, so we set it low, we go high, and then we set it back down. So we've done all of that right there. Now what we have to do, we don't start our timer now, because that ping does not immediately leave the sensor. We have to start our timer, our stopwatch, what? When the ping leaves the sensor. How do we know when the ping leaves the sensor? When we see the echo pin go high. All right. Now this is something that you've got to really think about to make sure that you understand it. You've got to think about it to make sure that you understand it. But what I am going to do is I need to what? I need to sit and wait. I need to sit and wait for the echo pin to go high. And so what do? I say while GPIO.input, what am I going to read from? Shall. That is not a command. Shall is not a command. While GPIO input, the input where? Of echo pin. So this is going to look at echo pin, and if echo pin, as long as echo pin is in the, or while GPIO echo pin is equals 0, as long as it is at 0, what do? Absolutely nothing. I just sit and hang here until I see the echo pin go high. So what do? I just pass. So it's going to get here, and if echo pin is low, it's just going to loop, 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 and do nothing. And then when it sees the echo pin go high, echo pin is no longer 0, and it's going to break out of this. So this is just a little place where your program hangs, waiting for the echo pin to go high, if that makes sense. Now, once that echo pin goes high, what do? I start my stopwatch, and I do that by grabbing the present system time. And so what I'm going to do is I am going to grab my system time by say echo start time is equal to time.time, which just gives me the system time. So now I've got a marker. I've got the time that the echo pin went high. All right, now what do I want to do? I just want to sit and see how long it stays high. So now I'm going to do while GPIO, or while GPIO dot input of echo pin, while that equals now what? 1. Okay, while that is equal to 1, what am I going to do? Okay, what am I going to do? Absolutely nothing. I'm going to wait. And so I'm going to hang here for as long as the echo pin is high. Then when the echo pin goes back low, now I need to what? I need to click my stopwatch again. And now I'm going to say echo stop time is equal to time again. So I've recorded when the pulse goes up, the echo pin goes up, and then I've recorded when the echo pin goes down. So echo start time and echo stop time. Now I have those two numbers. Now, how long was my ping in flight? How long was my ping in flight? What was my ping travel time? You guys tell me, what was my ping travel time? Well, it would be the echo stop time minus the echo start time, like that. Does that make sense? So now I know how long was the ping out there flying its journey. The ping travel time. Okay. Now what we're going to do is we're going to print ping travel time. Print ping travel time. All right. Now what I know is this number, like it's going to take like something like microseconds to milliseconds in order for the ping to make its journey. And if I just print ping travel time, it's going to be something like 0.000007 or something, 74365. And so you're going to have these numbers just going by, and they're going to be hard to read. So what I'm going to do is I am going to change that to an int, because then it will before I change it to an int, I'm going to report it in microseconds. So I'm going to take that small number and I'm going to multiply it by 1,000,000, which is 1e6. And now when it prints it out, it's not printing it out in seconds. It's printing it out in microseconds, and we should see numbers like 200 or 300 or 400 or 500. Okay, so that will be easier for us to read. Now, what else? Do we really want 200.346789325? No, we don't. And so now that whole thing, I'm going to make an int, And by making that whole thing an int, I should get an output that is readable. So hopefully it makes sense what I'm trying to do here. Now, you don't want to just sit and hammer this thing too hard, because you've got the pings going all over. And, you know, you might read, like you might send out a ping and it might go out and bounce off of something, and you send another ping and you could get like a second reflection of that first ping. So you really want to put a delay in here just so that you let the room quieten down. You let the room quieten down and you're not reading multiple echoes of that same ping. So I'm going to say time.sleep, and I'm going to sleep for 0.2 seconds. And then that should be good. Could this really be this easy? I think it could be. Now, what are we going to get? We're going to get a very simple but very valuable number, and that is how long the ping was out there doing its thing. I think we're ready to run this. Okay, somebody tell me how many mistakes I've made before I try to run this thing. I was really trying to be pretty careful. I sometimes get my case wrong. Sometimes I don't get my case right. But I will need you to hold your breath. And then you're looking down here to see if we're going to see some travel. But I guess what I should also do, yeah, let's go ahead and run it. Okay, hold your breath. Oh, keyboard interrupt. What is this keyboard interrupt? That looks so right. That looks so right. Invalid syntax. Except, what did I put a dot there for? Silly me, that should be a space. Let's try again. The real issue is one of you guys did not hold your breath. That was the real issue. So this time we're all going to hold our breath. Oh, GPIO. What is that? GPIO.bcm. Okay. GPIO.set mode. Wow, that sure looks right. GPIO not defined. Oh, I hope you guys saw that. As GPIO. You got to import it as GPIO. Okay, hold your breath. Boom, look at that. We are getting signals. Okay, we are getting signals. So at least the sensor is running. We have no idea whether these signals mean anything or not. We have no idea whether they're accurate or relevant, but it is good that we are actually getting a signal. And so I need to see, I think I'm going to get like a ruler out if I can find a handy dandy ruler. I love these little metallic rulers. There's a set of 3 of them that I have, but I'm going to get the big one. Okay. Now, as we get better at this, we're going to need to figure out, where do you measure from on the sensor? Is it the front of the cylinder, the back of the cylinder, the front of the sensor? You know, where is our 0 point as far as measuring distance? But what I'm going to do is I'm going to come over here, and you see these numbers that are going by down there. I'm going to give you a view where you don't see the program. You don't need to see that program anymore. But what you need to do is you need to see the numbers, and then you need to see my setup. So do you see the numbers going by up in the upper left? Okay, and now I'm going to put the ruler down here, and I think I should move this over. I should probably get smaller. I want you guys to see this well. Okay, so what I'm going to do is, if I look at this in inches, I like this ruler because it seems to measure to the very edge, but I'm going to measure from about the center of the cylinder. So you see, I'm not back against the base. I'm not at the front. I am at about the middle of the barrel. Okay, I'm at about the middle of the barrel. Now, I think what would make a good target, I think I will use our nice Bojack straight jumper wire box. And then I'm going to put this at 3. Okay, let's see if I put this at 3. That's not 3. That's 3, right about there. And also I'm going to go ahead and I'm going to scoot this over because I want to make sure that it has a good clear view of the target. And then I'm going to put it like that. Okay. And now look at that. We're reading about 385 milliseconds. We're reading about 385 milliseconds when when the target is 3 inches away. What if we go to about about 1.5 inches? We go from 385 down to about 284. Okay, so if I go to 1.5 inches, then there I'm getting about 159, which is about half of where we were before. You can see that I'm not getting the distance exactly right there because I don't have a real perfect view of it. But you see 235 is about half of where we were, before. So if you go there, and as I pull it back, the number gets bigger and bigger and bigger. Okay, and then as I move it forward, the number gets smaller and smaller and smaller. Why? The target is closer and the ping returns sooner. All right, now I can tell you that, let's say that if you're at about 3 inches, you should be expecting to see something like about 400. Okay, at about 3 inches, you should be seeing something at about 400, if that makes sense. Okay, now somebody tell me, so we now have ping travel time. Okay, we now have ping travel time. And that is what I was going to show you today, how to hook it up and how to get your measurement. Now I'm going to give you a homework assignment, and this homework assignment is going to be to use this number up here that is scrolling by, and to use that to calculate the distance to the target. So your homework assignment is to take this and to make a distance sensor. All right, now what does this require you to do? You see, this is more than just coding and hooking wires up. This is requiring you to think. Knowing the ping travel time, how do you calculate distance? All right. Some of you guys, this is really easy, but some of you guys, I'll give you a hint. If you're in your car and you're driving 60 miles an hour for 1 hour, how far do you go? 60 miles. If you're in your car traveling 60 miles per hour for 3 hours, how far did you go? Well, you went 180 miles. So in order to do this, what you need to know is you need to know the speed of sound. Okay, you need to know the speed of sound. And then what I want you to do is I want you to calculate the distance to the target in inches. All right. Now you're not going to be able to find a speed of sound very easily in inches per second or inches per microsecond. You're going to have to take the mile per hour speed and you're going to have to convert it to something that's in terms of inches. Does that make sense? So this is requiring a little thought and a little math, but this problem is not too hard for me to give you as a homework assignment. And so what I need you guys to do is I need you to do the homework, and then when you do the homework, I want you to post your solutions to YouTube. Then in my comments down below, link over to your project. I look at every single homework assignment that you guys turn in, and then in your description of your video, make sure that you link back to my video. So if someone stumbles on your video, they know what you're talking about, the homework assignment, the homework solution for this assignment. And then if you guys want to kind of try to do something a little more fancy or a little nicer, feel free to do that as well. But post your homework solution. The assignment is to measure distance from the sensor to the target, and then you got basically an electronic distance measuring system. Now, I will tell you that these little low-cost sensors like this, you can't go out and do 50 feet. I would imagine somewhere, somewhere. Also, you can't get tiny, tiny, tiny small, but somewhere between 1 inch and 1.5 inches to maybe 3 foot, 4 foot, maybe 7 feet, 8 feet. But you can play around with it and see what your useful range of your sensor is. I'll give you a couple of other quick tips here. One is make sure, like if you're measuring distance, make sure that your target is parallel to your sensor. So you don't want it off at an angle like this, because then are you measuring to here, or you're measuring to here, where you're measuring. So you want a nice, good target like that. And also on your sensor, make sure that it's not pointing down. Like if you plugged it in and it's pointing down, it could go down and hit the desk and skip off, and it could get on a strange path. So make sure that your sensor is coming out perpendicular to your board, straight up and down from your board. Okay, make sure that you're doing that. Get your sensor in there good. And then make sure that you've got a good target. Also, as you're doing this, make sure that you don't have some extraneous thing in the path, because it's going to bounce off of the first thing that it sees. Okay, guys, man, I hope you are having as much fun taking these lessons as I am making them. If you enjoy this video, be sure to give us a thumbs up. If you've not already, like and subscribe to the channel. When you subscribe, make sure you ring that bell, and then leave a comment down below. When the video's over, leave a comment down below to help me with the old YouTube juice, because the more people that interact, watch the video, like it, and comment, the more people that YouTube will show this video to. And that's important, because the world needs more people doing engineering and fewer people sitting around watching silly cat videos. Paul McWhorter with TopTechBoy.com. I will talk to you guys later.